All right, good afternoon.
Afternoon. How's it going?
Going okay. How's everyone doing out there?
Living.
Living's good. Well, welcome to week 7, and happy Valentine's Day if you're into that. And we are going to continue talking about mathematical induction today. And my rough plan for the rest of the quarter is something like induction, which we'll talk about today, and we may finish it today. We may go on to part of Wednesday's class, but we'll get through this this week for sure. I want to talk about recurrence relations, which is related to Fibonacci series, and we talked about these once already from kind of a high level. I want to dig a little deeper into them and relate them to induction. Week 8 will be a short week because Monday is a holiday, so we only have class next Wednesday. And we're going to... What do I want to talk about? We'll probably talk about counting. Talk about counting, something called the pigeonhole principle, sum rule, product rule, combinations, permutations, some statistics, all sorts of things like that. So that'll be week 8, and that may roll over a little bit into week 9. But week 9 I want to mainly talk about graphs and maybe a little bit about trees, although we're doing trees in CSE215 now. Graphs are a general version of trees, or trees are a specific type of graph. So we'll do some graph theory, and then at the end we'll do some automata theory. We'll look at language processing and parsing and grammars, and leading up to state machines, finite state machines, Turing machines, and some results about computability and what we can and cannot compute. And we'll get into some pretty interesting material in there. So definitely a full schedule from here on out, and we'll continue with induction today. But let's start off with any homework questions.
Yeah, I had a question on TA1, if we could go over it.
Sure.
Question 1, please.
So for the printing area, so you said to do, let me see if I can find it. I think it was like prime, or you print the number, then the prime, and then prime 1 minus n, I think. Every time I try to do that, it seems that like my number isn't printing out right. Like it's doing into the negatives.
So your goal is to print, something like, 6 equals 3 plus 3, 8 equals 3 plus 5, and so on. And so in your logic, right, you've got some function called, Goldbach do, takes an integer, prints it out as the sum of two primes. So for p equals 3 to n by 2, if p is prime and n minus p is prime, so n's the number we're trying to print, take consecutive odd numbers, and if that number is prime, and if n minus that number is prime, then we know that what? N is equal to p plus n minus p. Right? And these two if statements are checking that, make sure that's prime and that's prime. So print those out, %d equals %d plus %d. And maybe, np and n minus p, something like that. And if one of those is going negative, it should be, if this is going negative, right, just take a look at n and p and make sure n is bigger than p. I mean, p should only go from 3 up to n. N should be the number you're testing. And if something's printing weird, put in more print statements. Put in some print statements inside your loop and see what numbers you're testing for primality. And when you find one that's prime, print out a message and say, you know, this number is prime, and sort of break it down from that. Or better yet, use GDB, right? Hop in the debugger and see exactly what's what at the point where it's printing. And I'm guessing it's probably just, you know, something like switched somewhere order-wise, or something like that. All right, and then somebody had a question on the homework.
Yes, question 1, specifically about modular exponentiation.
Ah, good.
I was very curious as we were watching the videos, and is it only by 2s that we're counting down?
Correct.
Okay. Yeah, question 1, I have a feeling I got this totally wrong, but I don't know where I went wrong.
Why do you think you got it wrong?
Because I like to double check things using calculators.
Okay.
And I know that my end result isn't correct.
So we're looking for 2 to the 130th mod 7. So start with 2 to the first. That's just 2. 2 squared will be the square of that, which is 4. 2 to the fourth will be the square of this, which is 16, which modulo 7 is 2. And keep doing this, right, until you get up to 2 to the 128th. And at that point, right, you can use your calculator to check this and see if you got 2 to the 128th correct. If you didn't, say it. Yeah, go ahead.
While I was watching your videos, it looked like you're supposed to stop at when there's finally a remainder. 2 to the squared equaling 4 doesn't give you a remainder, so then you would move on to 2 to the 4 to the squared, at least according to what I was remembering from the video. So I'm kind of confused why.
So I think when we're talking about remainders, we were probably talking about greatest common factors, Euclid's algorithm, which is a different beast, because there's nothing really about remainders here other than, you know, these are remainders when you divide by 7. But we don't do anything other than write those down. So the goal in this first part is to find 2 raised to, you know, different powers, where each power is itself a power of 2. And so we find each of these by squaring the previous thing, because, for example, 2 to the 8th is the square of 2 to the 4th. And we found 2 to the 4th is 2, so this is just 2 squared. And we can calculate that by hand and say that's 4. And so that's calculating each of these powers of 2. And then you can test each of those in a calculator, and if this last one is right, probably the ones before it are also right. And then once we have those are our building blocks. Now 2 to the 130th will be 2 to the 128th plus 2. And the law of exponents says that's 2 to the 128th times 2 to the 2. And so you plug in whatever 2 to the 128th is, and you plug in whatever 2 to the 2 is, and multiply those, and then reduce that modulo 7, and you should get a number between 0 and 6. And if that final number is not right, it's got to be that one of these is not right, or you multiplied them incorrectly. So double check those on a calculator.
Another question.
Mm-hmm.
If the... I want to call them remainders, but I'm not sure what you want to call them, because they're like that 4 and that 2 and that 4 and that 2,
Mm-hmm.
they're all remainders. what if you're multiplying those together and they're much higher than the mod 7?
Then, so let's say we took 4 and 2 and multiplied them.
Mm-hmm.
That gives us 8.
So your remainder would be 1?
And 8 is congruent to 1 mod 7, exactly.
Okay. Okay, that makes more sense.
Okay, cool. All right, and then someone said for PA, would snips of our output main program on a PDF be okay? So your PDF has to contain all of the output on the test case, followed by all of your source code. All of that inside a single PDF. Does that make sense?
Sorry, could you say that again?
For PA1, the PDF that you're going to upload is going to contain all of the output for the given test case, right? The 500 number starting with 5 million, I think, followed by a copy of all of the source code for your program. And all of that is put inside one PDF file. That's the PDF that you upload. And yeah, you can just copy and paste to make that output file. I'm going to ask you not to use screenshots unless you're absolutely sure the screenshot is readable. Because it's a lot of output to put in a screenshot. It's going to be multiple screenshots. Easiest way to capture output go into a window. This is not PA4, but it's a way to generate some output, right? So let's say I wanted to put this into my file. Just go ahead and grab it with your mouse, right? Depending on whether you're using PuTTY or SSH or something, you can copy. You can set things up to automatically copy when you highlight and so on. But copy that, and then go into whatever your text processing tool of choice is, and just paste it. Just paste it right there, or paste unformatted if you want. And then you got nice clean output. If you want things to line up, pick a font that's proportionally spaced. So something monospaced, and now everything lines up nicely. So something like that. I was going to say, don't want to have to look up what library to use. Yeah, don't generate PDFs from C. That's a super ambitious way to do that. All right, good. Other questions? All right, well, we were doing induction examples, and we ended with that kind of funny example of tiling a floor with L-shaped tiles, and we saw that you can always do that if your room is 2 to the n by 2 to the n, and you have one missing square somewhere. And that was a hand-wavy, not a whole lot of math involved kind of example. Let's look at a kind of hand-wavy but more math type problem. Let's prove that n is less than 2 to the n for all n bigger than 0. So, 5 is less than 2 to the 5th. Well, that's pretty not surprising, right? 2 to the 5th is 32. This is just 5, right? 2 is less than 2 squared. 1 is less than 2 to the 1st, right? If n is 0, this is 0, this is 1. It's still true for 0. But here's a statement that for all n is less than 2 to the n. And we want to prove this using blinding sunlight and mathematical induction. All right, so we'll try this. So first thing we're going to do is we're going to express this as a family of propositions. So I'm going to say let P of n be the proposition n is less than 2 to the n. And notice it's this thing that I'm describing as a proposition, and my goal is to prove P of n for all n bigger than 0, or bigger than or equal to 1. It wouldn't make sense to say let P of n be the proposition n is less than 2 to the n for all n bigger than 0, right? This is what P of n says. P of 1 says 1 is less than 2 to the 1. P of 2 says 2 is less than 2 to the 2. P of 10 says 10 is less than 2 to the 10th. And so in order to prove that this is true for all n, we just have to prove P of n is true for all n. And we're going to do this with mathematical induction. So step 1, let's prove a base case P of 1. Well, P of 1 says 1 is less than 2 to the 1, and this is equal to 2, and 1 is less than 2. So we can see just by plugging in n equals 1 that P of 1 is true. So we've got a base case. That's usually not too bad. Second step, prove P of n implies P of n plus 1, where n is some integer bigger than 0. So we want to prove that if you know this, you also know that. And so this will be a little hand wavy because, do we know that 1 plus 1 equals 2, or do we have to prove that, right? Do we know that 1 is less than 2, or do we have to prove that? So this is a little loosey-goosey here, but I want to give you an idea of the inductive step here applied to an inequality. So let's start off with, P of n. That's a hypothesis. And because we're assuming P of n is true, we know that n is less than 2 to the n. That's the definition of P of n. What I want to do is I want to show that from these two steps I can prove P of n plus 1. So teacher's not allowed to look at this area. What I want to show is P of n plus 1. And this says n plus 1 is less than 2 to the n plus 1. So given this, I want to somehow show that. If I can do that, then I can say, I've proven P of n plus 1, so this follows, and then mathematical induction proves this original thing. So given this, how can I find this inequality? Well, we know some things about inequalities. We know if you add something to both sides, the inequality doesn't change. We know if you multiply by something positive, the inequality doesn't change. And we know that 2 to the n plus 1 is 2 times 2 to the n, which is also 2 to the n plus 2 to the n. So given this, can I somehow prove that n plus 1 is less than 2 to the n plus 2 to the n? And there's a variety of ways to do this, but let me just give you one that hopefully will be believable. N plus 1 is less than 2 to the n plus 1, which I get by just adding 1 to both sides. So, you know, add 1, preserve the less than sign. And since n is bigger than 0, right, n is bigger than or equal to 1, so 1 is less than or equal to n, which is less than 2 to the n, right? N is bigger than or equal to 0 by hypothesis. N is bigger than or equal to 1 by hypothesis. And n is less than 2 to the n. We've got that in statement 2. So we know that this is true, right? Because n is bigger than or equal to 0. And we've got statement 2. And so I'm going to extend my inequality and say n plus 1 is less than 2 to the n plus 1, which is less than 2 to the n plus. And if I put something in here that's bigger than or equal to 1, how jiggy do I want to get here? Let me do this more simply. 2 to the n is bigger than 1. And we know that because n is bigger than or equal to 1. Right, so forget those steps. N is bigger than or equal to 1, so 2 to the n is at least 2. And so this inequality up here, n plus 1 is less than 2 to the n plus 1, is less than 2 to the n plus, well, 2 to the n is bigger than 1, so it's less than 2 to the n plus 2 to the n. And that's just coming from 3 and 4. And now I'm going to, use what I foresaw in my ignore area and just rewrite this side n plus 1 is less than 2 to the n plus 1. And that's just, combining the two terms from statement 5. And this is what P of n plus 1 says. Therefore, P of n implies P of n plus 1, as long as n is bigger than 0. And therefore, P of n is true for all n bigger than or equal to 0. And that's mathematical induction from, our basis case and our inductive step. And that's what we were trying to show. So this is a different feel from the sum of integers examples that we did. And it's certainly different from the floor tiling. But the idea is similar. We assume P of n, and we do something to show that P of n plus 1 thus has to be true. And that's that inductive step that sort of makes the whole thing work. And if we give ourselves a little bit of slack, we can think about things like, prove 2 to the n is less than n factorial, where n is bigger than or equal to 4. So 16 is less than 4 factorial, which is 24. 32 is less than 5 factorial, which is 120. And you can sort of imagine the difference between factorials and powers of 2 is getting even bigger. And the intuition is, when we increase n, we multiply this side by 2, we multiply this side by n, something bigger than 2. And if this is, yeah.
That exclamation mark, what does it mean again?
That's factorial. So n factorial equals 1 times 2 times 3 times n. Or if you write it formally, product from I equals 1 to n of I. So it's the product of the first n integers.
So 4 exclamation point would be 1 times 2 times 3 times 4.
Correct. And factorials grow really, really quickly. If you get to 10 factorial, it's some number with several digits to it. 69 factorial, I think, used to be the biggest you could do on a pocket calculator, because it would be bigger than 10 to the 99th. And the intuition here is, this is 2 multiplied together n times. This is a bunch of stuff mostly bigger than 2 multiplied together n times. And induction, we're thinking about going from, n to n plus 1. We're thinking about, okay, I believe something is true for n. What happens if we go to the next case? Does this thing remain true? And if this is true for some number n, when we go to n plus 1, this left side will just get multiplied by another 2. But this right side get multiplied by n plus 1, which is at least 5. So when we go from n to n plus 1, this inequality is going to get even more unequal. And so, we could let P of n be the proposition 2 to the n is less than n factorial. And so if we assume P of n, we know that 2 to the n is less than n factorial. And then if we multiply both sides by 2, 2 to the n plus 1 is less than 2 times n factorial. And since n is certainly bigger than 2, 2 times n factorial is less than n plus 1 times n factorial. And this is n plus 1 factorial. And so pretty quickly from this you can get that, which is P of n plus 1. So there's formal stuff you have to do in the beginning, and you have to prove a base case, and there's stuff you have to do at the end here, where you say, therefore this thing and therefore that by mathematical induction. But the gist of it is basically mathematical induction is a tool that's letting us, if we can envision a way to move from one step to another, it's letting us sort of wave our hand and say, and you can keep doing that as many times as you like. Alright, so let's do one more mathy example related to divisibility. So here's a fun little fact. Let's prove that n cubed minus n is always divisible by 3, as long as n is bigger than 0. So prove n cubed minus n is a multiple of 3. Well, 1 cubed minus 1 is 0. That's a multiple of 3. 2 cubed minus 2, that's 8 minus 2 is 6. That's a multiple of 3. 3 cubed minus 3 is 27 minus 3 is 24. That's a multiple of 3. 4 cubed minus 4 is 64. Minus 4 is 60. That's a multiple of 3. So, we try some of these examples and it looks like it works. And there's a number of ways we can prove this, but we can prove this with mathematical induction pretty directly, although it takes some work. But it's a kind of direct process. It's knocking down a wall by hitting your head against it. The algorithm is very simple, but it takes a lot of work. So let's prove this with mathematical induction. So let P of n be the proposition 3 divides n cubed minus n. And we want to prove P of n for all n bigger than or equal to 1. Alright, so let's prove a base case. P of 1 says 3 divides 1 cubed minus 1. That's a 3. And we just have to note 1 cubed minus 1 equals 0, which is equal to 0 times 3. And so 3 does divide 1 cubed minus 1. And so P of 1 is true. So that's our base case, not too bad. Alright, inductive step. Prove P of n implies P of n plus 1. So first step, let's assume P of n, that's a hypothesis. Second step, let's write what P of n says. 3 divides n cubed minus n. That's the definition of P of n. And now we're at the point where we got to figure out what are we going to do here. And our goal is to show P of n plus 1. Well, P of n plus 1 says we want to show that 3 divides n plus 1 cubed minus n plus 1. And so a good question at this point is this true? I mean, if we're trying to prove this thing, we have to show that this is true. Well, why should this be true? I don't know. But let's just start playing with it. So I'm going to continue my ignore area, and I'm going to expand out what this thing over here is. Now, this is not part of my proof, right? This is scratch work. But let's write n plus 1 cubed minus n plus 1. Alright, so you got to do some algebra. Or you got to remember the binomial theorem, which we're going to talk about in a few weeks. N plus 1 cubed is n cubed plus 3n squared plus 3n plus 1. And we're going to subtract n plus 1, so we're going to subtract n minus 1. That's just algebra, right? Work it out, FOIL it 3 times or whatever, but you should end up with this. And this gives us n cubed plus 3n squared plus 2n, and then plus 1 minus 1 cancels each other. And our goal is to show that 3 divides this. Well, 3 certainly divides this. 3 times n squared, that's easy. So my goal now is to show that 3 divides n cubed plus 2n. And I've got no particularly good reason to believe this is true. But if I could show this, then I can work all of this backwards and eventually show that 3 divides this thing, which is P of n plus 1. Well, I don't necessarily see why 3 would divide n cubed plus 2n, but I have not yet used this. And I've got this in my bag of tricks. This is P of n. And to make this an inductive proof, usually you're going to use P of n to show P of n plus 1. If you can just prove P of n plus 1 without P of n, you don't need induction. But that's a lot harder to do. So I know this is true. I know that 3 divides n cubed minus n. And I want to show 3 divides n cubed plus 2n. And so I'm going to do a trick here. And this trick Maybe you have to see it the first time. Maybe some people figure it out. But here's a trick. We're gonna write 0 in a funny way. It's a classic math trick. You can write 0 as like, you know, blah minus blah. But sometimes that's useful. Alright, so I'm going to do the following. I'm going to say n cubed minus n is equal to n cubed minus n plus 3n minus 3n. N cubed minus n is the same as n cubed minus n plus 3n minus 3n. Why? Because this is equal to 0. And that's equal to that. But if I write n cubed minus n in this form, I can combine these two terms. Minus n plus 3n is plus 2n. And then there's my minus 3n. So my goal is to show this, right? 3 divides n cubed plus 2n. So anybody see how to connect this?
No idea, I just see an outlier, the negative 3n now.
There's an outlier in the negative 3, but I chose that because I know that this thing is divisible by 3. I may be going on a wild goose chase here, but I think we can get there.
I don't see it. I mean, I could see where, you know, the 3 divides n3 plus 2n is on that side of the equation. But I don't see what we could do with that.
So look at our original P of n. We know that 3 divides n cubed minus n. So we know n cubed minus n is equal to 3 times some integer k. Right? That's what it means when we said 3 divides n cubed minus n up here in step 2. Well, since this is equal to n cubed minus n, we can say n cubed plus 2n minus 3n is also equal to 3 times that same k, because this is exactly the same thing as n cubed minus n. And I can move that 3n from the left side to the right side and now say n cubed plus 2n equals 3 times k plus 3 times n, which is equal to 3 times k plus n. And all of a sudden, I've got n cubed plus 2n written as 3 times an integer.
Wait, can we back up a tiny little bit? Where did that 3k come from?
So up here in proposition 2, we stated that 3 divides n cubed minus n, which means n cubed minus n is equal to 3 times some integer. Right? That's the definition of divisibility. So this is another way of saying that 3 divides n cubed minus n. So then we we rewrite minus n as 2n minus 3n, and then we move the 3n over to this side and we combine, and now we've got n cubed plus 2n is equal to 3 times an integer, and so 3 divides n cubed plus 2n. And so there is a way to show this. Basically, we start here and we work through that. And once we know that this is true, then we can say that 3 divides 3n, 3 divides n cubed plus 2n, 3 divides this sum, which is n plus 1 cubed minus n plus 1. And then you take all of that and you bundle it back up and together and you move it from your ignore area over to here. and it's a whole bunch of algebraic manipulations that ultimately shows you 3 divides n plus 1 cubed minus n plus 1. Therefore, p of n plus 1, because that's what p of n plus 1 says. Therefore, Pn implies p of n plus 1. Therefore, using step 1 and 2 in mathematical induction, p of n is true for all n. And I don't want to get bogged down in the mechanics of this, right? My focus is the inductive mechanism that we're following in here. But the details of it, the way that we make this connection from Pn to Pn plus 1, that can change wildly depending on the problem. It could mean, you know, taking your tiles and cutting your floor into 4 quadrants and putting your tiles down. It could mean doing something with inequalities, looking at divisibility, doing a summation and substituting, all kinds of different forms. But for now, don't get tripped up on these details. Think about what's going on at a higher level. This way that we're making a bridge from something about n to something about n plus 1. So let's revisit one of our favorite examples, power sets. So if S is a finite set, then the number of things in the power set of S is equal to 2 raised to the number of things in S. So if a set has 4 elements, the power set should have 2 to the 4th, 16 elements. If a set has 10 elements, the power set should have 2 to the 10th, 1024 elements. And this is a theorem that we keep bumping up against throughout this course. It pops up in 250 because this is why we can count up to 2 to the n minus 1 with n bits. Right? Those bit strings can be viewed as subsets of a set containing n elements. So this is kind of a ubiquitous theorem that pops up in a lot of different forms. And we've seen some ways to demonstrate this. Let's see how we can prove this using mathematical induction. So let's make a family of propositions. Let P of n be the proposition which says a set with n elements has 2 to the n subsets. Alright, it's a proposition. Could be true, could be false. P of n says a set with n elements, any set with n elements has 2 to the n subsets. So let me say any. So P of 4 is the proposition that any set containing 4 elements has 16 subsets. And our goal is to prove P of n for all n, let's say bigger than or equal to 1. It's actually true for 0 also, but we'll just go with 1. So we'll stay away from the empty set. Alright, and we want to prove this using mathematical induction. So step 1 is the base case. So we want to prove P of 1. So what does the proposition P of 1 say, just in plain words? Somebody tell me.
A set with 1 element has 2 subsets.
Exactly. So P of 1 says a set with 1 element has 2 subsets.
Itself in the empty set?
Which are going to be itself in the empty set. And maybe, you know, we could fill a volume with mathematical gymnastics to prove this, but I'm going to take this as easy to demonstrate, right? If I have a set with some element, then the only possible subsets are the set itself and the empty set. So the power set of a thing containing one element has two elements, right? There's two subsets, the empty set and the set itself. And there can't be any other subsets because there's only one element, right? So if that element is included in the subset, it's this. And if the element's not included, the subset is empty. So we're going to take this as being true. And like I say, you know, if we were in a cafe in France and we were at the turn of the century, previous century, we could probably have a glorious long discussion about this and walk away unsure. But we're just going to take this as, you know, easy to demonstrate. P of 0 would be even easier, but then we got to deal with power set of the empty set, and I don't want to do that. So we're going to take P of 1 is true. And now, to do our inductive proof, we need to prove P of n implies P of n plus 1. And this is for some n bigger than or equal to 1. All right, so, and I'm going to do this in kind of a hand-wavy way, okay? And we're going to get hand-wavy for a bit. So let S be any set with n plus 1 elements. All right, we're trying to prove that a set with n plus 1 elements has 2 to the n plus 1 subsets. All right, so I'm going to say, okay, start with any set S that has n plus 1 elements. All right, and I'm going to say, you know, let T be a subset of S. And there's two possibilities. All right, before I name these two possibilities, I'm going to do something very controversial. I'm going to say, let A be some element of S. I'm going to pick one element from S. We know n's at least 1, so n plus 1 is at least 2. So there's at least 2 elements in S. I'm just going to pick one of those elements, and I'm going to call it A. All right, and I'm going to pick, you know, any subset T, subset of S. There's two possibilities. Exactly one of these two things is true. Either A is contained in that subset I picked, or A is not contained in that subset I picked. Everybody agree with that? Beginning of the problem, I've got my set S. I'm picking one magic element, A. Just some element. And now, if you give me any subset, there's exactly one of these two statements is true. Either the element A is in that set, or it's not in that set. So the first question is, how many possible subsets are there that do not contain that element A? So how many subsets of S do not contain that one element A? Any idea? Close. It's related to n.
I was going to say an infinite amount, but that's not right, I don't think.
Yeah, so S contains n plus 1 elements.
What's A? A is a part of...
A is some element that I picked in the beginning of the problem. It's some element of S.
So that should just be n minus 1 or something like that.
Something like that. So here's how we can answer this, right? I'm looking for subsets of S that do not contain A. Any subset of S that does not contain A is also a subset of this set. Right? If I take the set S and I remove A, right, and I take a subset of that, well, it's a subset of S that doesn't contain A. And any subset of S not containing A is a subset of this set. And any subset of this set will be a subset of S and will not contain A. And so the number of subsets of S that don't contain A is the same as the number of subsets of this. Well, how many elements are in S minus A? That's just n. Because S has n plus 1 elements in it. Right? So S is a set with n plus 1 elements. If I throw away one of those elements, I'm left with a set with n elements. And by my inductive hypothesis, if I have a set with n elements, the number of subsets is 2 to the n. So how many subsets do not contain A? Well, the same as the number of subsets of this set, which by our inductive hypothesis is just 2 to the n. So I have 2 to the n subsets of S that do not contain A. And then I can ask how many subsets of S do contain A. Well, any subset of S containing A is exactly a subset of this with an A tossed in. And since I have 2 to the n subsets of this, I have 2 to the n subsets that do contain A. And since every subset of S either contains A or does not contain A, the total number of subsets is 2 to the n plus 2 to the n, which is 2 to the n plus 1. And so if you wave your hands enough of that at that and write it up, any set with n plus 1 elements will contain 2 to the n plus 1 subsets. And that means P of n plus 1 is true. And so given P of n, we can prove P of n plus 1. That's our inductive step. You tie it all together. Therefore, P of n is true for all n.
Do we have any homework like this? Because I literally have no idea what's going on.
You're going to get a whole bunch of homework questions on induction with a bunch of these examples. So there's a couple of ways to try to understand this. One is the mechanics, right? The question of, as we're going from one step to another, can we nod our heads and agree that that's a valid step? The second question is, why does this succession of steps prove what we're trying to prove? The third question is, how do we know that this is the succession of steps we should follow? And those are increasingly difficult, right? The first level of understanding is to be able to follow a proof and say, you know, yeah, that makes sense. Okay, that follows from the previous thing. This follows also. Okay, yeah, each of these steps seems legit. That's the first level. And for these, that gets kind of wonky at times, but for other things like the sums of integers, for example, that we were doing, those can be more direct in some cases. The second level is, if you accept all of this, do you believe that that proves the thing that we're trying to show? Right? And that's a question about the essence of a mathematical inductive proof, right? If we prove a base case and we prove an inductive step, do we believe that that proves our family of propositions for all n, for example, bigger than 1? And then the question of how do we know what this succession of steps should be when we're doing this ourselves, that's going to come from practice. And we'll have lots of problems to practice on. And most of them will not be as weird as this. But let's try. And the ultimate goal here is not to be able to do inductive proofs. It's to be able to understand recursion. So let's try a different kind of example here that will tie in to algorithms. So let's look at deMorgan's theorem. And so basic deMorgan's theorem, engineering 250, is something like that. Well, this is a set theory version, but you know, the union of A and B is the same as complement of A intersect complement of B. Actually, let's do it in engineering 250 style. So A and B negated is negation of A ORed with negation of B. All right, everybody remember that from 250?
Plus? Oh yeah, times is plus.
Yeah, that's an and that's an or.
Right, okay.
All right.
Just in a wall.
Yeah. So let me write this in a more general form. Let's say A1, A2 bar equals A1 bar or A2 bar. So that's also deMorgan's theorem. I'm just naming my variables differently. All right. So we're gonna take that as given, and we sometimes use a more powerful version of that, which looks like this. And I don't know if you've done this in 250 or not, but this turns out to be true. I can have a 3-input NAND gate, and I can evaluate it by having a 3-input OR gate with inverted inputs. So if this is given to us, is this true? Does this follow from that? Could we prove it? And we could do it with a truth table, but without a truth table, could we prove it some other way? And it turns out it's not too hard. So we're not talking induction for a minute, right? We're just talking engineering 250. We're told, you know, by me or by Izad or by someone, this is a true theorem. We have this thing called deMorgan's theorem. This is equal to that. And now we're asked, you know, on a test, can we show that this is equal to that? And let me show you a way that you can do this. So A1, A2, A3 bar. Well, this is the same as A1, A2, ANDed with A3, all barred. I can, you know, AND these in any order that I want. And so I've got, you know, this thing ANDed with this thing, and I'm taking the complement. And deMorgan's theorem, DMT, tells me that if I AND two things and complement, that's the same as taking the first thing, complementing it, taking the second thing, complementing it, and ORing. So that's just plain old, you know, two-variable deMorgan's theorem. But I can also use deMorgan's theorem and say this expression right here can be written as A1 bar or A2 bar. And I can just keep my A3 bar. And bingo! There we go. We showed that this was equal to that. So that might take some trial and error the first time, but once you've seen it and done it a few times, if someone, you know, challenges you, can you prove that this is equal to that? Yeah, just use, you know, plain old deMorgan's theorem and, you know, break these two so that these two things are grouped together, And, you know, that gets you to here and it gets you to there. Now, suppose someone comes up to you the next day and says, can you prove that this is equal to A1 bar or A2 bar or A3 bar or A4 bar? Can you prove the four variable version of deMorgan's theorem?
Yeah.
So how would you do it?
I would separate 1 and 2 and separate 3 and 4.
So we could separate A1 and 2 and separate 3 and 4. But let me do something a little different. Let me do... What you described will work perfectly, but I want to do something slightly different so that we can generalize it. I'm just going to separate everything except the last one. I'm going to group all those first terms and say this is equal to this. And then I'm going to use plain old deMorgan's theorem of two variables and say this is this, ORed with that. And now, since I've already shown deMorgan's theorem of three variables, I'm going to say this is equal to this.
Someone's audio jamming.
And then that's going to go to A4 bar.
Multiple people's audio is duplicating your own.
Alright, I just muted everybody, but if you want to talk, go ahead and open up your mic. So the and of four terms negated, I'm going to group those first three, right, which is just, you know, doing these three things first. And then I'm going to use two variable deMorgan and say, you know, this ANDed with this negated, well, it's this negated, ORed with that negated. And then I'm going to use my previous result about, you know, the three variable version of deMorgan's to say this is the same as this. And that's going to prove my four variable version. Okay, and we're going to go one more level. Suppose someone says, all right, you think you're really good, huh? I bet you can't do this. Show me that that is the same thing as, you know, the OR of 5 inverses. And I'm going to do exactly the same thing. I'm going to take those first four and group them together. This is certainly the same as that, right? Because an AND, it doesn't matter what order I do these in. I'm going to use two variable deMorgan's theorem and say, well, that's the complement of the first thing. ORed with the complement of the second thing. But since I've already proven the four variable version of deMorgan's, I know that this thing on the left I can rewrite as this. And then this is, you know, just the A5 bar. And I'm done. I've proven that, you know, the NAND of 5 variables is the same as the OR of 5 complemented variables. So does everybody agree with this? Does everybody see that, you know, if we believe deMorgan's theorem up here, we can pretty easily demonstrate this 3 variable version. And using this, we can very easily show the 4 variable. And using this, we can easily show the 5 variable version. Does anybody have any doubts or questions about this so far?
Yeah, I have doubts. I think you should prove to us that you can use deMorgan's theorem with 20 factors right now.
So yeah, this is the next question, right? Suppose someone wants you to prove the 20 variable version of deMorgan's theorem. So, I mean, you could get more sheets of paper and using this prove the 6 variable, and then using that prove the 7 variable, and so on. But you understand that, like, you know, there's nothing magic. When I get up to 8 variables, this process is not suddenly going to break, right? We can see that. We just take everything except the last one, group it together, use the previous version of deMorgan, plus the 2 variable version of deMorgan, and this is going to fall out. So this is a case where, you know, looking at this, proving this, you know, first few versions of this, we're pretty convinced if we wanted to do this for 1,000 variables, we could do it. But first we'd have to do it for 999 variables, and before that we'd have to do it for 998, and so on. So mathematical induction is a way to generalize this process, but make it very formal. to basically show how we would do this 1,000 times to get up to, the case of 1,000 variables, or 1,000,000 times to get up to the case of 1,000,000 variables. So if you see something and you believe that you could replicate that process, to higher and higher versions of this statement, in this case, our variable n is how many terms we're using. And if we can see, how we would go from 3 to 4, from 4 to 5, from 5 to 6, and that we know we could keep doing that till we got up to 1,000,000, right? All we have to do is somehow formally say, how do you get from n to n plus 1? If we know deMorgan's is true for n variables, how do we know it's true for n plus 1? And if we can demonstrate that, in other words, if we can prove the inductive step, then mathematical induction lets us say, okay, I don't have to do this all the way up to 1,000,000. The fact that I can get from n to n plus 1, that's enough to say, yeah, I can do this and I can get up to 1,000,000. That's the essence of mathematical induction and why it's such a powerful technique. And it ties into programming, it ties into algorithm development and all these other things, because a lot of times we can see a way to move from one step to another. We don't necessarily want to do this 1,000,000 times, but we know that we could. And so induction gives us a way to take that intuition that we could do this 1,000,000 times, and it lets us formalize it. All right, so think about that. Let's take a 5-minute break, and we'll come back, and then we'll do a fairly formal, a somewhat formal mathematical proof, proof using mathematical induction that deMorgan's theorem is true for n variables. That will basically be built around how we move from one step to another. And so in this case, we're starting with the intuition, and then we're going to build a proof around that, instead of trying to build a proof and looking for the intuition. So we'll come back in, what time is it? It's 14:08. Come back in about 4.5 minutes, and we'll play around with that. All right, we're back. By the way, if you go onto my YouTube channel, so these aren't part of the playlist, but if you just go onto my channel and do a search, I've got several examples of mathematical induction that I work out in detail. These are from a few years ago, and so slightly different presentation, but you know, some ideas on why mathematical induction is a thing, some examples, an example we're going to go through this afternoon also with postage stamps, and then kind of a cautionary video of what not to do in an inductive proof. And these are, you know, like, I mean, 3 minutes, 5 minutes, 7 minutes. They're not terribly long, but you can search through my channel for those if you like. And that's another presentation of it. This is also in the textbook, by the way, so there's some more examples, and there's a ton of problems in section 3.8 and at the end of chapter 3 in the supplementary exercises, and half of the problems have solutions in the back of the book. So there should be good opportunity in there to find some sample problems and get some practice, in addition to the homework that I'll post on Wednesday. All right. So let's prove deMorgan's theorem for n variables. And so we'll start with a family of propositions. Let P of n be the proposition. And this is going to be, you know, A1, A2, dot, 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 AN bar equals A1 bar or A2 bar or dot, 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 or AN bar. So that's, you know, the statement of deMorgan's theorem for n variables. And our goal is to prove P of n for n is bigger than or equal to 2. Let's stick to notation. Prove P of n for all n bigger than or equal to 2. Okay, base case. P of 2 is just deMorgan's theorem, which we're going to assume we know. Okay, so we take an engineering 250, we passed, so we believe and we know deMorgan's theorem is true for 2 variables. So A1, A2 bar is A1 bar or A2 bar. So let's concentrate on the inductive step. Let's prove P of n implies P of n plus 1. And what I'm going to do is exactly what I did here, to go from one step to the next step. So I'm going to say, you know, A1, A2, A3, dot, 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 AN minus 2, AN minus 1, AN, all barred, equals, and I'm going to group these first n minus 1 terms together. I'm going to do this in a different order. A1, A2, A3, dot, 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 AN minus 2, AN minus 1, AN. Right? So this is equal to this because I just grouped these things together. And this is going to be equal to, and I'm going to use deMorgan's theorem of 2 variables, which is, you know, says that this ANDed with this, negated, is the same thing as the first thing negated. ORed with the second thing negated. That's just deMorgan's theorem. So the negation of this whole big long AND term is the negation of this, ORed with the negation of that. All right, bear with me. Let me be a little more careful here. let me do it like this. Let me go up to n plus 1. So this is equal to a1, a2, dot, 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 an, added with an plus 1 bar. And that's equal to a1, a2, dot, 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 an bar, ORed with an plus 1 bar. And that's deMorgan's theorem. All right, so that's our first step. And our goal is to prove P of n implies P of n plus 1. Okay, so I'm going to say P of n is true. That's a hypothesis. And P of n is the proposition that the NAND of n terms is the OR of those n terms complemented. So P of n tells me a1, a2, dot, 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 an bar equals a1 bar or a2 bar or dot, 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 or an bar. That's the definition of P of n. Well, this is that. And now I'm just going to substitute this into there. And that's going to tell me a1, a2, dot, 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 an plus 1 bar equals. And instead of writing a1, a2, an bar, I'm going to substitute this a1 plus a2 plus dot, 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 plus an bar plus an plus 1. And that's just substituting 3 into 1. Right? And this is exactly what we did by hand when we wanted to go from, say, 3 variables to 4 variables. We grouped those first 3. We used plain old deMorgan's theorem, and then we replaced this with an OR using the previous version of deMorgan's theorem. Well, that's all that's happening here. I've stated, the left side of this for n plus 1 variables. I broke these into 2 pieces. I used plain old deMorgan's to break this into, a big long NAND, ORed with something. And then I used Pn, the fact that deMorgan's works on n variables, to rewrite this as that. Well, now I'm done. I've proven that the NAND of n plus 1 variables is the OR of those n plus 1 inverted variables. That's P of n plus 1. Right? Statement 4, proposition 4 is P of n plus 1. Therefore, P of n implies P of n plus 1. Therefore, P of n for all n bigger than or equal to 2. And that's what we wanted to show. So the takeaway here is this idea that, sometimes if we want to show something is always true, we can try to show it for a few cases, and if we can see a way that we would move from one case to another, then we can capture that way in a formal proof using mathematical induction. If we can see why adding one element to a set doubles the number of subsets, right? We can capture that in an inductive proof, and that's what that example of the power set was. If you have a set, certain number of subsets, if you add one element to the set, you double the number of subsets. Because you have all the subsets of the original set, and you have each of those subsets with that one new element added in. So if we start counting subsets, every time you add another element, you double the number of subsets. So here's a set AB. The power set consists of the empty set, the singleton A, the singleton B, and the original set. 1, 2, 3, 4 elements. If I move to a set A, B, C, and I want to construct the power set, what are all the subsets of here? Well, it's exactly the subsets of AB and the subsets of AB that also include a C. And those are the only possible subsets. If I add a fourth element D to here, what subsets am I going to find? Well, all of these will still be subsets, and all of these with a D tossed in will also be subsets. And so however many subsets I have of this, when I add another element, I'm going to have twice as many subsets. And so if I start building up sets by adding elements, I get this intuitive sense that each time I add another element, I double the number of subsets. And since, you know, a set containing a single element, the power set has 2 subsets. If I had a second element, I'm going to double it to 4. If I had a third element, I'm going to double that to 8. That gives me this intuitive idea that, you know, the power set contains 2 raised to the number of things in the set. And that gives us the insight for how to construct this mathematical proof. So this is a way to formalize our intuition that we can show something in a general case. But that comes back and it ties into algorithms. So let's look at a different kind of question. So this is called a postage stamp question. So given an unlimited number of 5-cent and 3-cent stamps, prove you can make any postage of 8 cents or more. So this is a different kind of question. Got an unlimited pile of 3-cent stamps and an unlimited pile of 5-cent stamps. And you want to mail something and you need 137 cents worth of postage. Can you make exactly 137 cents by using some combination of 5s and 3s? That's the question. And the claim is, yes, you can. You can make any postage 8 cents or more exactly with some combination of 5-cent and 3-cent stamps.
As all numbers above 8 are either a multiple of 3 or 5.
Well, 11 is not. Right? 11 is not a multiple of 3 or 5.
3, 5, or...
In fact, 11 is prime. But we can still do it. We could do a 5 and 2 3s. So let's prove this. So let's make a family of propositions. Let P of n be the prop. You can make n cents postage using 3-cent and 5-cent stamps. And we want to prove P of n for all n bigger than or equal to 8. Alright, so start with a base case. Let's prove P of 8. So can you make 8 cents postage using 3-cent and 5-cent stamps?
Yes, 3 and 5.
Yeah. So 8 equals 3 plus 5. So P of 8 is true. Right? We found a way to answer the requirements of P of 8, which is to make 8 cents postage using 3 cent and 5 cent stamps. Use a 3 cent and a 5 cent, you got 8 cents. So P of 8 is definitely true. So we've got a base case. All right, so let's go on to the inductive step. Prove P of n implies P of n plus 1. All right, so step 1, P of n. That's the hypothesis. Step 2, you can make n cents from 3 cent and 5 cent stamps. That's what P of n says. So we're taking as given we can make n cents postage, right? Using 3 cent and 5 cent stamps. And by the way, n is bigger than or equal to 8 here. All right. We're going to do something really weird here. We're going to break this into two possible situations. All right. So consider a solution for n cents postage. P of n tells us there is a way to make n cents using 3 cent and 5 cent stamps. All right, so consider some solution for giving us n cents out of 3 cent and 5 cent stamps. There's two possibilities. Possibility 1. That solution, say if that solution includes a 5 cent stamp. So if the solution for n cents includes a 5 cent stamp, replace it with a pair of 3 cent stamps. So peel that 5 cent stamp off the package, put two 3 cent stamps on it. What happens to our total postage?
It's 1 cent over.
It's 1 cent over. So we had a solution for n cents. We replaced the 5 cent with two 3 cent stamps. Now we have n plus 1 cents. So if our solution for n cents includes a 5 cent stamp, we can find a solution for n plus 1. But there's another possibility. If that solution does not include any 5 cent stamps, then there's no 5 cent stamp we can peel off to replace with two 3s. Well, we know n is at least 8. If n is 8, there's a solution with a 5 cent stamp. So if the only solutions don't include 5 cent stamps, n must be bigger than or equal to 9. And if there's no 5 cent stamps, solution uses only 3 cent stamps. And since n is at least 9, our solution uses at least 3 3 cent stamps. And so replace 3 3 cents with 2 5 cents. In other words, if there's no 5 cent stamps in the postage on our n cent envelope, right, we know there's going to be at least 3 3 cent stamps. Peel those off, replace it with 2 5 cents. We've taken off 3 3 cents, we've added 2 5 cents. What's happened to our total postage?
N plus 1 again.
It's n plus 1. And those are the only possibilities. Our solution includes at least one 5 cent stamp, or it does not include any 5 cent stamps. And in either case, we have an algorithm to generate n plus 1 cents worth of postage. Therefore, the proposition is true for n plus 1. And so Pn implies Pn plus 1. Therefore, by mathematical induction, Pn is true for all n bigger than or equal to 8. And we're done. Okay, so do you believe this proof? Do you believe that these are the only possibilities? Either our solution for n cents includes at least one 5-cent, or it doesn't include any 5-cent stamps. And if you believe that, do you agree that, you know, if there's a 5-cent stamp, we can replace it with 2 3s and increase our postage by 1? Or if there's no 5-cent stamps, we can replace 3 of our 3 cents with 2 5-cents and increase our postage by 1. And so in either situation, we can take the solution for n cents and construct from that a solution for n plus 1 cents. And if you buy those arguments, right, then in the language of our family of propositions, right, P of n says that there's a solution for n cents. If we believe there's a solution for n, we've shown there's a solution for n plus 1. And so we've proven this. We've proven a base case by example. And if we believe mathematical induction, therefore, P of n must be true for all n bigger than or equal to 8. In other words, we can always make exact postage using only 3-cent and 5-cent stamps for any amount of postage, 8 cents or more. So before we go on from here, any questions or doubts or concerns about this? And one thing blatantly missing from this is the motivation, right? How do you know to do this? And that's, you know, somebody else figures that out. But after we do a few of these, you'll be able to do these too. But ignoring the question of how did you know to do this or that and so on. Any questions about this or doubts about the legitimacy of it?
No, it makes sense. Yeah, just the path is to get to this solution is confusing. So.
Yeah, the path is kind of elusive. All right, so here's the cool thing. We've proven that there is always a way to make n cents postage out of 3s and 5s. But we've also uncovered an algorithm for doing that. So suppose somebody asks us to make 13 cents postage. Using 3s and 5s. And, you know, we could trial and error. We could say 2 5s and a 3. But suppose we don't know that. Suppose we're being lazy, and we're like, yeah, I'll give you a solution. Come back next week, and I'll have a solution for you. And what do? We turn to a friend, and we ask our friend, hey, can you make 12 cents postage using 3-cent and 5-cent stamps? And they say, sure, and they come back to us a few days later, and they say, okay, here's your solution. And we say thanks. And we know that our solution was if you have 3 3s, replace them with 2 5s. Well, there's our solution to the 13 question, 3 plus 5 plus 5. So as long as we have a friend who can answer a simpler version of the question, right? Someone comes to us and wants a solution to 13. We turn to a friend who can work, you know, up to 12. We say, give us a solution for 12 cents. They give us that solution, we can turn it into another solution for 13. Now, how does this person answer the question? They turn to another friend and they say, hey, can you give me the answer for 11 cents? And the person who does that is going to come back to them and say, yeah, do 3 plus 3 plus 5. This person's going to take that answer, 3 plus 3 plus 5, and they're going to apply the algorithm. If you have a 5, replace it with a pair of 3s. And there's the solution to 12, and they give that to me, and I use that to get the solution to 13. And how does this person get the answer? They ask somebody else, hey, can you make 10 cents postage using 3s and 5s? And the person says, yeah, do a 5 plus 5. And they take that solution and they use the same algorithm. If you have a 5, replace it with a pair of 3s. There's their solution. And how did the person over here get the answer for 10 cents? They asked somebody, how do you get 9 cents postage? And the person said, do this. And they took that solution. And it didn't have any 5s, so they took 3 3s and replaced it with 2 5s. And that's where they got their solution. Alright, and way down on the other side of town, we're at this person who wanted the solution for 9 stamps. They found a friend and said, hey, can you make 8 cents postage? And what did that person do? They looked at their inductive set and said, yeah, I can do that. It's just 3 plus 5. They didn't have to turn to a friend. They just said, take 3 cents and 5 cents. And the person doing 9 took that solution and then said, oh, if you got a 5 cent, replace it with a pair of 3s. So the only one who actually solved this problem without turning to somebody else was the person who solved this one. And they have, a post-it note on the wall that says, 8 cents equals 3 plus 5. So they don't have to go to a friend who can do 7. They have a solution, and they give that solution to this person, and that person changes it into a solution that they hand to this person. And they've got 10 from 5 plus 5, and they give that to this person, and they change that into a solution for 11, and so on. And the way we code this is we use one function which calculates postage using 3 cent and 5 cent stamps, and we call ourselves. We use recursion. Alright, so let's look at a different version of this and I'll show you some code. We can do the same thing with 3 cent and 7 cent stamps, where we want to make at least 17 cents postage. So how would we do this? If two cases. One, if you have at least 2 3 cent stamps, replace those 2 3 cents with a 7 cent. Right, peel off the 3 cents, which brings down 6 cents in postage, and then put a 7 cent stamp on, so it brings up your postage by 1. All right, possibility 2. You don't have at least 2 3 cent stamps. So you have either 1 3 cent stamp or you have no 3 cent stamps. Well, since your total postage is at least 17, if your solution has 1 3 cent stamp, you have at least 14 cents made from 7 cent stamps. If you have no 3-cent stamps in your solution, you have at least 17 cents made from 7-cent stamps. But if you have one 3-cent stamp on your package and your total postage was at least 17, you've got at least 14 cents made from 7-cent stamps. And so you have at least 2 7-cent stamps. So replace 2 7-cent with 5 3-cents. You peel off 14 cents, you add 15 cents, your postage has gone up by 1. All right, so this would be the heart of an inductive proof of this problem, right? We'd say, you know, suppose you have at least 17-cent stamps, and suppose you've proven this proposition for n, and then we'd have two possibilities. If you have two 3-cent stamps, replace the solution for n, right? In the solution for n, replace 2 of those 3 cents with a 7. Now your postage is n plus 1. If you don't have at least 2 3 cents, then your solution for n has at least 2 7 cents. Remove those, replace it with 5 3 cents. Now your solution has a postage of n plus 1. And so we can show P of n implies P of n plus 1. Well, we can turn that pretty readily into an algorithm. So here's a C program that implements a function called solve. It says how many stamps do we want, and it will tell me how many 3-cent and how many 7-cent stamps I need. And the way I'm going to use this, I've got a main program. It's going to ask me what my total desired postage is. I'll put in a number. I'll convert it to an integer. I'm going to call that total. And if the total is less than 17, I'm not going to play. Otherwise, I'm going to call my solve algorithm, ask it how many 3-cent and 7-cent stamps, then I'll print out the number of 3 and 7-cent stamps. And I'll just do that in a loop. So, you know, if I want 20-cent stamps, it'll say 2 3s and 2 7s. If I want 50 cents postage, it'll say do 5 3s and 5 7s, so 15 and 35. If I want some big long number, it'll be, you know, 10,329 7-cent stamps and 3 3-cent stamps. So I've taken a proof using mathematical induction to demonstrate that there is always a solution, and I've turned that proof into an algorithm for finding that solution. So how does this algorithm work? Here's my solve function. If the total is less than or equal to 17, I'm not even going to try this. So this is just, you know, so I don't do anything ridiculous. All right. But if my total is 17, right, I've got a hardwired solution. 2 7s and a 3. Right? So that's our base case. If I'm trying to do this for some number bigger than 17, I've got two possibilities. Okay, the first thing I do is I solve it for n minus 1. And I find how many 3-cent and 7-cent stamps get me one less penny than I want. And now there's two possibilities. If I have at least 2 3-cent stamps, I take off those 2 and I increase the number of 7-cent stamps. That's my solution. So that's this case right here. If you have at least 2 3-cent stamps, get rid of those and replace it with a 7. So that's what's happening here. Take off 2 3s, add 1 7. Otherwise, I know that I have at least 2 7-cent stamps. And so decrease the number of 7s by 2, increase the number of 3s by 5. And bingo, I got a solution to my problem. So there's this kind of parallel dance going on, right? Between proving that an algorithm is correct, proving that a problem can be solved, and creating an algorithm that actually solves it. Now, if I started with this algorithm, if I just kind of, you know, woke up from a nap and I suddenly realized how to make postage using 3 and 7-cent stamps, and I coded this algorithm, and then I wanted to know, is this algorithm correct? I can prove it. How do I prove it? With mathematical induction. It would look exactly like a mathematical inductive proof of P of n. And so induction will let us prove correctness of algorithms in some cases. All right, don't get tripped up on the pointer stuff here that C makes you do so you can pass values back. But this is a direct implementation of, you know, these two steps. Replace 2 3s with a 7, or replace 2 7s with 5 3s. So there we replace 2 3s with a 7, or we replace 2 7s with 5 3s.
This is a very interesting question.
Okay.
No, I'm just saying, like, this
Oh, this is. I thought you were saying you had one. Okay. Yeah. And postage stamp questions are a popular topic in induction, but they're not magic per se.
I am curious about something.
Yeah.
Is this under the assumption that this will always reach the number you're looking for, or that it will be over or maybe a little less than the number you're looking for sometimes?
This is trying to always reach exactly the number you're looking for.
Basically uses funky ways of incrementing it by 1.
Yeah.
Until it finds the right one.
Mm-hmm.
By subtracting the numbers for 3 cents and 7 cents, or adding them.
Yeah, yeah. And so we can do this with a lot of different things. So here's a function for calculating powers of 2. So I can say, you know, what's 2 to the 7th? 2 to the 7th is 128. What's 2 to the 4th? 2 to the 4th is 16. So what does my function look like? I have a function called 2 to the n. And if n is 0, I know 2 to the 0 is 1. Otherwise, 2 to the n is just 2 times 2 to the n minus 1. Right? It's a recursive definition. And it's built on this algebraic fact that 2 to the n is equal to 2 times 2 to the n minus 1. That's as long as n is bigger than 1, bigger than or equal to 1. I don't want to find 2 to the 0 like this, because it'll say it's 2 times 2 to the minus 1, and 2 to the minus 1 would be 2 times 2 to the minus 2, and so on. So I'm hardwiring a base case. I'm saying if you want 2 to the 0, just return 1. Otherwise, return 2 times 2 to the n minus 1. And there's no while loop, there's no for loop, there's no counting, there's no running product I have to save. But nonetheless, this function does calculate 2 to the n. How could I prove that this function always works? I could make a proposition. P of n is the proposition that this function returns 2 to the n. And I could try to prove P of n is true for all n bigger than or equal to 0. And I would have a base case. If n is 0, I can see that this function is correct because 2 to the 0 returns 1, which is the right value. And if I know that 2 to the n works correctly for n minus 1, I'm guaranteed it works correctly for n, because it returns 2 times 2 to the n minus 1. So a simple inductive proof, kind of simple, inductive proof would prove that this algorithm works correctly. Here's a way to calculate the length of a string. So how do you tell how long a string is? Well, if the string ends with if this first character is a null terminator, the string has no length. Otherwise, the length of the string is 1 plus the length of the string starting with the second character. So what does this look like? I want to know how long the string hello is. Well, it's just 1 plus the length of ELLO. And how do I know what the length of ELLO is? It's 1 plus the length of LLO. And what's the length of LLO? It's 1 plus the length of LO. And what's the length of LO? It's 1 plus the length of just the string O. And what's the length of the string O? It's 1 plus the length of an empty string. And my base case tells me the length of an empty string is 0. So after I've made all these calls and I come back, this function is going to return 1 plus 1 plus 1 plus 1 plus 1 is going to return 5. But it's a 2-line length function. There's no looping, there's no, while string bracket I is not equal to null terminator I plus plus or any of that stuff. It's just, if the string's empty, return a 0, otherwise return 1 plus the length of, and this is how we get to the string starting with the second character. And this works fine. But how would we prove that it works? P of n would be the proposition that mylen returns the length of a string of n characters. P of 0 is clearly true because if the string has length 0, this if condition will be true and it'll return 0. And if this works for a string of length n, a string of length n plus 1, the function will return 1 plus whatever the function returns on that substring, which has length n, which by our hypothesis returns n. And so this function will return n plus 1 for a string of length n plus 1. Yeah, and that last postage stamp question, we assumed the postage had to be at least 17. So if you try it with something smaller, it says please try again. But for 17 it works, and for higher.
What are some other neat combinations that this works with?
Well, in well-designed currency systems, it always works. Now we have pennies in our currency, so you can always make any amount with enough pennies. But if you had only like 2-cent and 4-cent stamps, you wouldn't be able to make any odd amount of postage. That would be a sort of poor choice. But most systems of currency, if you look at the denominations, they should be able to get you any amount of money that you want. But like I say, if you have pennies, it's totally easy to do. But even without pennies, there's cases. So there's lots of different examples of this. Most ones that you think of, you can do, and certainly anything that's relatively prime, I think you can prove that at least beyond some point, it's always possible to get any postage.
Oh, because of the sum of any number can be, or any number can be created by the sum of two primes, whatever.
I believe so, and actually by any two relatively prime numbers, I think also. You can get to that with Euclid's algorithm and some other properties. but I don't know what characteristics you need for this not to be doable, for there to be postages you can't get to. I think there has to be a common factor, maybe. It's an interesting question. All right, so let me mention one more concept, which is strong induction. There should be a space there. So so regular mathematical induction, the way we've been doing this, looks like this. Given P of 1 and P of n implies P of n plus 1, we can conclude P of n for all n bigger than or equal to 1. So that's mathematical induction. There's another version of this called strong mathematical induction. And in strong mathematical induction, you're given P of 1, and you're also told that if you have P of 1 and P of 2 and P of 3 and everything up to P of n, you can get P of n plus 1. Then you can conclude P of n for all n bigger than or equal to 1. All right, what's the deal here? To prove something with plain mathematical induction, all we have to do is prove that if you're given n, P of n, you can get P of n plus 1. With strong induction, we're not just told that P of n is true, but we're also allowed to consider that P of n minus 1, n minus 2, all the way down to P of 1, all of these are true. And we only have to show that if all of these are true, we can prove P of n plus 1. And certainly if all of these are true, P of n is true. And so if we can prove that P of n by itself gets you P of n plus 1, right, we can certainly prove that having P of n plus a bunch of other stuff will get you there. But this is sometimes easier to prove. You've got more stuff in the hypothesis. If you think of how you would write a proof, right, you would state each of these as a hypothesis. You got more stuff in your bag of tricks, right, that you can use to try to prove P of n plus 1. So proving this strong inductive step is usually easier than just proving, you know, the regular inductive step. And certainly if we know this is true, right, then we know that this follows, because if this is true, we can use P of 1 to prove P of 2. And then we know P of 1 and P of 2 are true, and so that will give us P of 3. And if we know 1, 2, and 3, that will give us P of 4, and so on. So if we believe mathematical induction, we certainly have to believe strong mathematical induction. But it's sometimes easier to prove something using this. So let me get an example of this. Prove that all integers bigger than or equal to 2 can be written as a product of primes, possibly including itself. So, you know, 10 is 2 times 5, 11 is just 11, and so on. And so let P of n be the proposition n can be written as a product of primes. And so P of 2 is true because 2 is just 2 and 2 is prime. And so we want to prove that given all of these, we can prove P of n plus 1. In other words, we're not just assuming that n can be written as a product of primes. We're assuming that every number less than or equal to n can be written as a product of primes. And with all of that in our hypothesis, we just want to show n plus 1 can also be written as a product of primes. And with all of these things in our toolbox, it's pretty trivial. because there's two cases. Case 1, n plus 1 is prime. And we can just write n plus 1 as, you know, n plus 1. Right? 17 is just 17. That's written as a product of primes. It's 1 prime, right? So that's easy. The trickier case is, you know, n plus 1 is not prime. So it has some factors different from 1 in itself. So write it as a times b, right, where a and b are bigger than 1 and less than n plus 1. Because that's what it means to be not prime. You can write it as a product of two things other than itself and 1. Well, since a is bigger than 1 and less than n plus 1, p of a tells us that a equals, you know, some product of primes. And b is also bigger than 1 and less than n plus 1, and so p of b says b is equal to, you know, another product of primes. And so a times b, which is equal to n plus 1, is just the product of this first set of primes times the second set of primes. And bingo, we've written n plus 1 as a product of primes. Therefore, p of n plus 1 is true. So if we know every number smaller than n plus 1 can be written as a product of primes, either n plus 1 is prime and we're done, or n plus 1 is a product of two numbers smaller than n plus 1, and each of those can be written as a product of primes. And so you multiply those two products together, you got another product of primes that gets you n plus 1. So strong induction is useful sometimes.
And computers are great at it?
Yeah, can be. All right, let me leave you with one parting thought. We got 5 minutes here. Let's prove n is equal to n plus 1 for all n bigger than or equal to 2. Which, if we can actually prove this, there's a problem. So I'm going to call this a false proof. But let's prove n equals n plus 1. So I'm going to make a family of propositions. Let p of n be the proposition n equals n plus 1, where n is some number bigger than or equal to 2. Alright, and we're going to prove p of n implies p of n plus 1. So step 1, I'm going to assume p of n, that's our hypothesis. Step 2, I'm going to state what that means, which says n equals n plus 1. That's the definition of p of n. I'm going to add 1 to both sides. That's just algebra. If n equals n plus 1 should be equal to n plus 1 plus 1. Well, this statement right here, this is p of n plus 1. P of n plus 1 would be the proposition that n plus 1 equals n plus 1 plus 1. Well, we just stated that that was true. So we've proven p of n plus 1. Therefore, p of n implies p of n plus 1, n bigger or equal to 2. Therefore, p of n for all n bigger than or equal to 2. And we just broke mathematics. We just proved every number is equal to itself plus 1. So what did I do wrong?
Concluded the end result?
Well, but I mean, I followed the steps of mathematical induction, right? I don't have to know that P of n is true. I just have to show that if P of n is true, P of n plus 1 is also true. And I've done that. Right? If n equals n plus 1, then in fact n plus 1 does equal n plus 1 plus 1. Because I can add 1 to both sides. And this is absolutely true. There's no problem there. But there's clearly some problem with being able to prove P of n. So what did I mess up?
Your original hypothesis?
My hypothesis is well defined. It's the proposition that n equals n plus 1. And to prove this implies that, I'm going to assume the hypothesis and then work logically using nothing sneaky and prove P of n plus 1. So I'm going to leave you with that and kick it around, and we'll talk Wednesday about why we did not break math. But think about that. Don't get too hung up on it, but go back and look at it once in a while, or play around with it and see if you can figure out what's going on there. All right, come by office hours if you got questions with the homework. Remember, the homework's on number theory, GCDs, primes, that kind of stuff. So, and I'll post homework for Wednesday, probably tomorrow, and that'll be some induction problems. So I think Wednesday we're set to go on and talk about recurrence relations. So we'll continue from there. All right, have a good afternoon. I will see everybody next time.